Okay, so what we're looking at is section 1.8 from the PowerPoint slides. Oh, now let's see here. Matthew says, do you have the PowerPoint slides open because we don't see them? I do have them open. Let me see. Hold on. Let me see here. So once again, in MyMathLab under Multimedia Library, you can get PowerPoint slides, ebook, and so forth for the different sections. Okay. So now that I have them up, I have to bring them in. Thank you, Arthur. I think that is the issue. I have to go back into share. Here we go. There we go. Okay, so now we're good. Can everybody see the PowerPoint slides? Wonderful, wonderful. Okay, so hold on here now. I gotta make sure I'm in the right thing. All right, so from the beginning. Okay, so it's no different than like when you learned about functions like f of x equals x squared. You're mapping, you know, you have a domain and a range, Well, we can take vectors and transform vectors into new spaces. And you have a transformation of a vector x, that's called the range of t. Okay, and you have a domain, which is where the vector lives. So a nice picture is right here. Here you have a space, a domain space in Rn, where the vectors live, where the vector x lives, and you can transform the vector by, for instance, taking the vector x and multiplying it by a, pre-multiplying it by a. So if x is an n by 1 vector, so long as A is an m by n matrix, you're going to transform the vector x into the transformed vector x will be a new vector, the transformed vector x, that's going to be in the M space. So basically, if you take an m by n matrix A and multiply it by an n by 1 vector, you're going to get then an m by 1 vector in the transformed space, Rm. Okay, so that it's very interesting. I mean, you're used to taking numbers and mapping them. You know, you map a domain into a range, but it's always, you know, R being mapped to R. Well, with vectors, you can map vectors in one dimension to vectors in another dimension. Okay, so are there any questions on the figure here, on the picture? All right, well, let's continue then. Let's continue. Let me just see here what I want to see what you're seeing. Okay, you're seeing exactly what I'm seeing. Hold on here. Okay, Solomon, I'll explain that. Yes, I'll re-explain that, no problem. Let me just hold on here. Gotta go, right, I'm back in here. Good, okay. So you see here in the picture, you're, all right, let me show it to you in another way here. We'll go back to the slides, don't worry. But let me bring up the whiteboard here. So let's say that you have a vector or matrix. A matrix, say, that looks like this. Now, what are the dimensions on A? How many rows, how many columns? That's right, 2 by 3. So you have a 2 by 3 matrix. Now you want to take the matrix A and multiply it by a vector x. In order for the matrix multiplication to be properly defined, what would the dimensions be on x? What's the dimensions on x have to be? That's right. It's going to be it has to be something by 1 because it's a vector. So it's going to be 3 by 1. Okay. So you could take a vector, thank you, like 1, 0, minus 1. Okay. When you take a 2 by 3 matrix times a 3 by 1 matrix or 3 by 1 vector, what's the dimensions going to be on your result? It's got to be a 2 by 1. It's got to be a 2 by 1 because the column number on matrix A matches the row number on the vector x, but then what's left is a 2 by 1. And the 2 by 1 matrix, and you've done this kind of thing before, you've done taking a matrix and multiplying it by a vector. Let's see, what's the value going to be here? It's going to be, well, I mean, let's see, it's going to be 1 times 1 plus 2 times 0 plus 3 times -1. So, hold on, one moment. When in doubt, I'm going to write it out, right? So 1 times 1 plus 2 times 0 plus 3 times -1 should get a -2 on the top. And then on the bottom, you should get a -4, right, on the bottom. Because 0 times 1 is 0 plus -1 times 0, that's 0 plus 4 times -1. So what happened is you took this vector x, okay, that lives in 3-dimensional space, and you mapped it into this transformed vector x. Okay, you mapped it into this transformed vector x. That lives in R2. Okay, so you've taken a vector that lives in R3 and mapped it into a vector that lives in R2. Okay, so that's what that figure is. That's a concrete example to show you what they're talking about in the figure. Solomon, are you all right with that? And I know there may have been other questions, but is that okay? All right. Well, let me show you here, and we may have a few, let me see here, -2, how do we get that? This is something that you go 1 times 1. That's right, Binyam, 1 times 1 plus 2 times 0. I'll show you the top one. I'll let the other one for you. How do we get -2? 1 times 1 plus 2 times 0 plus 3 times -1. So this is something I want you to, we can talk about this a little more during our classwork time. But this is how we got the first number here, the -2. So, you take the first row and multiply it by that column, number by number. And so since you use the first row and that first column there of X, there's only one column, the number in the resulting matrix in the first row, first column is as you see it. Okay, great. Well, let me get back to the slides then. Hold on here. So this is, hold on. We gotta, please be sure now, everybody, that you do work on use those extensions and complete the homework that you've not completed so that you're comfortable with things. Okay, comfortable with the concepts. Very good questions. Very good questions. Now hold on here. I got to get to these slides. Okay. So now we continue on here, and this is basically the matrix transformations. This emphasizes exactly what I told you. You can transform a vector from one space to another space. So I'm going to just kind of move along here. All right, I'm going to move along here. And, well, let me just see here. Okay, I'm going to move along. I want to get, okay, so there's a lot of good things here, but I'm going to cover these things in examples. So, okay. Let me talk about a transformation. I want to go to example 3. So again, I'm going to follow up this PowerPoint. I'm not doing every PowerPoint slide, but I'm going to follow up things with a few examples. So example 3 says, let A be the matrix 1, 3, 0, 1. The transformation, okay, this transformation defined by A times X is called a shear transformation. So the transformation, since we have a 2 by 2 matrix, it's going to map vectors in R2 to other vectors in R2. That makes sense. Okay, and it can be shown that if the transformation acts on each point in the square in figure 4, then the set of images forms the shaded parallelogram. Let me show you that. So what they've done is the matrix is 1, 3, 0, 1. And they're saying that if you were to multiply the matrix, let's say you were to multiply the matrix by the 4 corners here in this square, okay? If you were to do that, then the resulting transformation is going to give you an image that's going to be a parallelogram. Okay, so you're mapping points on this square to the transformation of the points on the square will be the points on this parallelogram. And one thing they do is they say, okay, well, let's pick a point. Let's pick a point like 0, 2. Okay, let's pick one of the corners. If we take 0, 2 and multiply it by 1, 3, 0, 1, you're going to get the coordinate 6, 2. Okay, and 6, 2 is going to be one of the corners. It's going to be one of the corners of the parallelogram. If you look at the top line segment, the left-hand corner on the top line segment in the parallelogram will correspond to the coordinate 6, 2. Okay, so you can transform, if you were to use this matrix, this matrix and multiply it by every one of the corners, you would get the 4 corners of the parallelogram. Okay, under the transformation. Okay, that's what this example is talking about. And, you know, really to feel this very well, you almost have to do some problems on your own. And I'm hoping to give you some class time for that. All right, so another thing too they talk about here, and this is, you know, again, emphasizes things in the book, is something called a linear transformation. So a transformation is linear if you can take, well, also, let me just go back here. If we go back to the parallelogram, they also show that the image of 2, 2 is going to be 8, 2. Because if you multiply the matrix A by 2, 2, you get 8, 2. So that means that if the corner here, 2, 2, gets mapped to 8, 2. So what they did was they transformed two of the corners on the square and showed you where they landed in the parallelogram, the corners on the parallelogram. And if you were to do all four corners, transform them, you would get the four corners of the parallelogram. But let's continue on here. Let's continue on. So a transformation is going to be linear if the transformation of the sum of two vectors is equal to the sum of the transformations of the vectors. Okay, similarly, the second condition for a transformation to be a linear transformation is if the transformation of a constant times vector u equals the constant times the transformation of u. Okay, these are some rules for linear transformation. And you might wonder, well, why is this important? Well, let me show you why. Let me show you why. All right, so let me bring back here. Hold on here. Let me go back into our thing here. I want to now stop sharing the slides and go back to the whiteboard and write in the two rules for linear transformation. The first one was that the transformation of the sum of two vectors is equal to the transformation of the first vector u plus the transformation, and I'm trying to draw this the best I can, plus the transformation of the second vector v. So this is a fairly abstract definition of a linear transformation, and in linear algebra is probably it's maybe one of the first courses you've seen that can be this abstract. But let's make it concrete. So my question is, when I see this, and when I see the second rule that says the transformation of a constant times a vector u, that can be written as a constant times the transform vector u. Okay, and these two conditions are what's required for a linear transformation. Okay, the first thing that comes in mind, okay, and I'm noticing here we have 31 people in attendance. I have 28 students. I have 31 participants, so we may have a couple visitors. Hello, visitors, if you're visiting. All right, so okay. James, okay, hello. And well, what I'm saying, Matthew, is normally we have 28 people in attendance. And with me, that makes 29, but we have 31 people. So, you know, welcome anybody who's not in the class, you know, welcome. You never know. It might be the head of the college that's here. You never know. All right. All right. So I see these two. I see, you know, these two rules and these two rules make a linear transformation. But why is that important? Why is that important? How can that be related to what we're learning here? Well, if you think about matrix, well, let me say this the right way. Think about a transformation on a vector defined by A times X. Okay, think about that. Okay, I mean, we're used to taking a vector and multiplying it by a matrix X, assuming, you know, that is a linear transformation. Now, why is that? Why is that? Well, because if you were to say, okay, transformation of U plus V, transformation of U plus V, okay, well, that equals A, matrix A, times the sum of the vectors U plus V. But remember, matrix multiplication is distributive. So this is going to equal A times U plus A times V. Okay, you can, when you multiply a matrix A times vectors U and V, matrix multiplication is distributive. And you'll actually formally see that in the theorem later. But how many are like comfortable with this? How many of you know are very comfortable with this? This is maybe something they've seen before. Yeah, I mean it's common sense in a way. Thank you, everybody. Well, and so what do we have here? Thank you, everybody. We have the transformation of U plus the transformation of V. So the first condition here is satisfied. The second condition says if we transform constant times U, well, okay, so what would that be here? That would be taking the matrix A and multiplying it by C times U. Okay, but it turns out that constants can be brought out front of, can be brought out like this. And so A times a scalar, so C times U, C is a scalar, there's no vector symbol above it. So A times C times U is equal to C times A times U. And that just equals C times the transformation of, because A times U is the transformation of U. That's how we, you know, that's how it's defined here, right? So now the second condition is satisfied. So whenever we multiply or pre-multiply a vector X by a matrix A, that is a linear transformation. And so any properties that are satisfied by a linear transformation will be satisfied for A times X. Okay, are there any questions on that? Any questions? So A times X, if you define your transformation to be equal to A times X, then that is a legitimate linear transformation. That is correct. In linear transformations, you'll see in section 1.9 that linear transformations have a very nice property. You'll see it in theorem, you've seen two properties. Thank you, Matthew. You've seen two properties there. But there are, I'm gonna just stop there with that. So are there any other questions before we go to a few examples? Section 1.8 is on the test, yes, because that's covered. That'll be due on Thursday, yes. Okay, are there any other questions? Okay, and of course this is going to be in our recording if you need to refer to it. All right, let me bring up a few examples here. One moment here. Okay, I'm bringing it up there. So, Mikkel, I will be very clear on the exam where I would expect you to use technology. I will be clear on that. Yes. Yes. You're welcome. Okay, so let us look at an example here. So I gave you a guided tour, good guided tour of section 1.8. Now let's look at an example here. Let me give you a moment to copy the example down. One moment. Okay, so Mikkel asks, are the range and span interchangeable? No. Well, gosh, hold on. Hold on. I want to be a little careful about answering that. Don't worry. I want to be a little bit careful about that. Let's see here. Well, the matrix A times the vector X can be written as a linear combination of the column vectors of A. And so this, let's see here. It's an excellent question. I hadn't really thought about it heavily before. if B is in the range of the linear transformation of A, I'm sorry, if B is in the range of this linear transformation where the vector x is being mapped to A times x, that means that B would have to be in the span of the column vectors of A. That B would be in the span of the column vectors of A if B is in the range of this linear transformation. Okay, is that, Mikhail, comfortable with that? And the reason we know that is because the A times x, you learned back earlier in one of the earlier sections that when you take a matrix times a vector, that matrix multiplication is equivalent to a linear combination of the column vectors of x, where the weights on each vector are from the vector x. So yeah, so span would imply a linear combination of the column vectors of A. Good, good. So now, well, so what we have to do, you're welcome, you're welcome. What we have to do is see if there's some vector x, when we multiply A times x, will it equal B? Okay, that's what we have to do. Okay, so let's look at the solution. Let's look at the solution. Is B in the range of, let's see, I want to say this, all right, let me just go to the solution here. So the question is, does there exist an x such that A times x equals B? Okay, does there exist a vector x such that A times x equals B? Yes, and the augmented matrix would include B. That's right, Binyam, absolutely. Absolutely. Okay, so take a moment to copy this down. All right, so let's remember what's going on here. So A times x is our transformation. That's how we're defining our transformation. So what we're doing, and of course, x would have to be a 4x1 vector. So what we're doing for the matrix product to be defined. So what we're doing is we're taking the vectors, x vectors that live in our 4, and we're transforming them into these transform vectors. Where do the transform vectors live? In what space do they live? Well, I'm not worried about B yet. Hold on, though. Hold on. I'm trying to give a little context to what I'm saying is B in the range. Hold on. Is B in the range? Hold on here. of the linear transformation, the linear transformation takes vectors x that live in R4 and maps them into new vectors in R3. So what I'm wondering is the vector b in this space? And I want to say also that this space here, really R3, right, is a bigger space than what the transform space is. The transform space is a subset of R3. Okay, it's a subset of R3. But I want to know if B is in that space. Okay, this space here, which is a subset of R3. Okay, so I want to make sure that you're getting the context right here. I want to make sure you're understanding what I'm saying here. We all agree that if we take a vector x in R4 under this transformation, it's going to be mapped into some subspace of R3. Okay, that's what I'm saying. Are we okay with that? All right, good. Well, and what we want to know is the vector b in the subspace? The vector b lives in R3, but is it a member of the club? Is it a member of this subspace that's being created by this transformation? So to find out, I have to see if there's a vector x that gets mapped into this vector b. So we're going to solve the augmented matrix AB. Okay, and if you do row operations on this, you'll see that the augmented matrix AB, okay, reduces to this matrix, this augmented matrix in reduced echelon form. And last time we talked about how you can use MATLAB to, to get a matrix in reduced row echelon form. Okay, and certainly, we want to use technology for some of our big matrices, some of the more difficult ones, and of course, most of the matrices you're going to be dealing with are going to be not too big, but still, we want to know how to use technology, right? All right, so the matrices that aren't too big, it doesn't take row operations. It's important to remember our row operations because you'll find it's important to always understand the elementary row operations and not forget how to do them. But certainly we do want to use MATLAB as well. Okay, so what do you think? What do you think about our augmented matrix? Does it have a solution? Does our system have a solution based on that augmented matrix? Yes, absolutely, Binyam. It does have a solution. Okay, and because we have a solution, this means then that the matrix B, and there are free variables, but that's right, Matthew, but nevertheless, we have a solution. So that means that therefore, and I'll move to the next page if that's okay. Is anybody still copying? X3 and X4 are free variables. That's absolutely right. We have two free variables. And may I move to the next page? Okay, all right. So since B is in the range of A, okay, I want to be careful here. I don't think I wrote that right. B is in the range of, let me just make sure. I don't want to say A. I want to say our linear transformation. I'm just going to say B is in the range. I mean, you have it, you wrote it out more formally. B is in the range because the augmented matrix, the system, is consistent. We have a consistent system. Oh, you're right. There should be no arrow over A. Thank you. The arrow should be over B. Thank you. Good catch, Binyam. Thank you. There's no arrow over there. Hey, look, I'm going to finally use this white. Look, I'm going to white this out. Look at this. Is Dr. Duty good or what? There we go. So B is in the range because our system is consistent. We have a consistent system. I didn't even bother to solve it. I know that B is in the range of A because we have a consistent system, and so there are vectors of X that will map into the vector B. And as a matter of fact, how many? There's going to be an infinite number of vectors that get mapped into B. Okay, and so this is the kind of thinking that's going to go on with the section 1.8 questions. All right, are there any questions? Are there any questions at all?
What would be the solution X?
Well, you'd have to solve the system, to get the good question, to get the solution X. But we could do that, but it's not really necessary here. But we could do that, and if we did that, if we actually found the vector X, and if we wrote it out like in parametric vector form, we could actually, well, we would know what solutions look like that map into X. But for this problem, we just wanted to know if B was in the solutions that map into B. But for this problem, we just wanted to know if B was in the range. So that's right, Sega. Good question. Yoel, you're okay with that? You all right?
I think so.
Okay, all right. Sega says when there's consistency and free variables in the solution, sure, B is in the range. But you don't need free variables. If you had if you had a system where you actually solved for like X wasn't, the solution X didn't have free variables. Let's say the solution X were just one solution, then B would also be in the range. All you need is to get a solution for X, a consistent system. It doesn't matter if you have free variables or okay, great. Well, let's look at another question here. Let's look at another question. All right, so let's move on then. Everybody's got this copied okay? Are there any, I want to make sure I'm pacing myself well. All right, very good, very good. Oh wait, hold on, Matthew wants to, all right, one moment. Okay, no problem at all. All right, well, let's move on here. Okay, let's look at another problem, something a little more, this is a little more theoretical, but I know it comes up in your homework, and you know, I try to do a variety of problems. All right, let me give you a moment to copy this down. While you're copying, I just have a question. Is Michael Betry here? Michael Betry? I hope maybe you're one of the two callers calling in, Michael Betry. Maybe. All right, well, hopefully he'll come back if he's not. Wait, there was a question here. Hold on. So Sega, well, all right, trivial solutions are like if, all right, so Noah wrote A times X equals 0. So trivial solutions would be solutions where, like the vector X equals the 0 vector. That's a trivial solution. Okay, a trivial solution. So you're always solving, A times X, you're solving a system of equations that can be written as like normally when we talk about trivial solutions, we think about homogeneous systems of equations, A times X equals 0, as Noah has written there in the chat window. So if the vector X equals a 0 vector, if all your x1, x2, all your variable x's are zeros, that's the trivial solution. Otherwise, if that's not the case, you have a non-trivial solution. Okay, Sega, does that make sense? Okay, great. Okay. All right, so now here we are. What we have here in this problem are unit vectors. unit vectors. And how many maybe in physics or even in calculus 3, if you've taken multivariable calculus, have seen, okay, Matthew knows what I'm talking about, like I is equal to the vector 1, 0. Okay, many of you, good. And then J is equal to the vector 0, 1, wonderful. Okay, well, in this course, rather than use, I mean, at least for this, at least for now, rather than use I and J, okay, we use E1 and E2. So E1 is the 1, 0 vector, E2 is the 0, 1 vector. And what you're being told in this problem, you're being given vectors y1 and y2, and all you're told is that you have a transformation that maps the vector e1 into y1 and the vector e2 into y2. That's all you're told, and they want you to find out the correct image, the correct mapping of the vector 4, negative 4. Okay? So this problem is a problem that relies on your knowledge of the two conditions for linear transformation, those two conditions we talked about. So I'd like to move to the solution. Are there any questions so far? Okay, everybody's copied it down okay? Okay, thank you, Matthew. Thank you, Christy. Okay, so normally you would think of this, and normally you would think, well, man, I don't know what to do here, It's not clear what to do, but the problem is a problem that in order to do it, you have to use the properties of a linear transformation. So to that end, let's go to the solution. The first thing we want to do is we want to write the vector 4, negative 4 as 4 times the e1 vector plus negative 4 times the e2 vector. I mean, certainly we can do that. All right. There's a reason why we're doing this. Okay, so one thing I'm going to note here is that 4e1, I could think of that as vector u, and negative 4e2, I could think of that as vector v. Okay. What's the transformation of u plus v? Can we rewrite that, being that we know the transformation t is a linear transformation? That's right, Binyam. Very good. Transformation of u plus the transformation of v. That's what we do. And that's by the first property of a linear transformation. I don't know why that shows that line there, but I'm not going to worry about it. I'll remove it in a moment, but I want to. Well, I'll just. Here's you. Here's V. U. And V. We got U and V here. So the transformation of U plus V here is equal to the transformation of U plus the transformation of V there. Now what property are we going to use? We got to do a little bit more here. Got to do a little bit more. Can we factor out the constants from the transformation? That's right. Solomon, that's right. We can. Yep, Robin's right. Binyam's right. Absolutely, we can do that. And so then, by the second property for a linear transformation, we're going to get 4 times the transformation of E1 plus -4 times the transformation of E2. And now we're good, because we were told that E1, the vector E1, maps into Y1. And the vector E2, under the transformation, maps into the vector Y2. That's right. That's right, Binyam. Absolutely. And so now, you know what Y1 and Y2 are, and now you can solve the problem. Okay, are there any questions? Any questions? I would say all of it, Matthew. Matthew's saying how much work should we show on the test? When in doubt, show it all. That way you'll be sure that you're showing all the work. Okay. I mean, you are linear algebra students. You are not lazy students, right? And you know for the exam that I need to see that you understand the concepts, so I need to see your work. If you get a problem right and there's no work, I can't give you credit, right? I have to see the work. Now, yes. All right, are there any questions before we move on? All right, I'll stop the recording then.